Picking up where we left off, radiation notes part 2. Remember, a black body is any object that absorbs a radiation and then re-emits the same amount of energy it absorbed. So pretty much anything that is considered a black body. And again, temperature is the measure of the amount of motion of particles. Faster motion, higher temperature. All right, so the intensity then is the amount of radiation given off at a given time. So if you got the top line, you got 4 photons given off together. That's more intense than 1 photon of light. More waves given off makes it more intense, makes it more energetic. Shorter wavelengths also are more energetic. If you stand up and you're holding a rope and it's fastened to a tree at the other end and you're making waves, if you're going slow with a little bit of energy, you've got long wavelengths. But you speed up and you put more energy into it, now your wavelengths shorten in size and the frequency of those wavelengths increases, giving you more energy. Okay, as temperature increases in an object, or as energy increases, the frequencies and intensities also increase. And I just explained that kind of, you can see yourself doing that with the rope. So the wavelengths get shorter as temperatures increase and the frequencies come higher. So at absolute zero, where there's no energy, that means even atoms stop. They cease to move. That is negative 273 Celsius or negative 459 Fahrenheit. That is no energy, nothing moving. So Kelvin is degrees Celsius plus 273. So you can joke with your parents and say, tell your parents you are hot, and tell them you are 310 hot, because your body temperature is 32 degrees, 37 degrees Celsius. So absolute zero is the lack of energy. Up there you see Kelvin is degrees Celsius plus 273. Know that. 273, negative 273 is lack of energy. That's good to know because we've got some equations we're going to throw this in. The black body curve represents the intensity of radiation emitted by any heated object. For instance, you, being a human being, like me and other people on Earth, we mainly give off infrared heat. But if you look at our black body curve, the peak of which we give off is the most thing we give off. But you can see leading up to that peak, we also give off a little bit of other stuff, like a little bit of microwave, a little bit of radio, a little bit of TV, but really negligible to pick up. So the wavelength of the main emission, the main amount of emission, the peak emission, is related to temperature. So we got a little thing called Wien's law. The total amount of energy given off increases as temperature increases. So we apply Wien's law. There's the black body curve. Wien's law says that the wavelength, the maximum wavelength of intensity, is equal to 0.29 centimeters, that should be centimeters up there, divided by temperature in Kelvin. So the wavelength in centimeters is equal to 0.29 centimeters. There it is. So 0.29 centimeters divided by temperature in Kelvin is your wavelength maximum. So our sun, if you plugged our sun into it, let's see, I've got it coming up soon. The hotter the object, the bluer or the shorter the wavelength it is. So Rigel, that blue star we saw on the top of Orion, is blue. Betelgeuse on the other side, opposite it, is orangish red. So obviously Rigel is hotter because it gives off blue light, and Betelgeuse is orangey or red, so it gives off cooler. It's a cooler planet. All right, so there's temperatures. If you're 600 degrees Kelvin, that's still pretty hot. You're not giving off light yet. If you're 6,000 Kelvin, you're giving off light. If you're 60,000 Kelvin, you're giving off ultraviolet, or probably X-rays and gamma rays down there. All right. As temperature increases, the total amount of energy radiated by the object increases exponentially. So a guy named Stefan came up with this. It is basically the flux, F is energy flux, how much energy is given off at a certain moment, is equal to the Stefan-Boltzmann constant. So that little symbol there is a constant, times temperature to the fourth power. So if you double your temperature, 2 to the fourth power is 2 times 2 is 4 times 2 is 8 times 2 is 16. You've given off 16 times the amount more energy. So F is the total amount of energy called the flux. T is the temperature in Kelvin. And the symbol is the Stefan-Boltzmann constant, which, do not memorize that. I'll put that on the test. 5.67 times 10 to the minus 8th watts per meter squared, Kelvin to the fourth. That way the Kelvins cancel out and it comes up in joules. So Stefan's law basically says the total energy related is proportional to its temperature to the fourth power. So if an object is twice as hot, like I said, how much more energy does it give off? We'll plug it in. Cancel out the constants. The x's will cancel out. 2 to the fourth power is 16. 1 to the fourth, 1x to the fourth power is 1. So it's 16 times more powerful. Boom. Know how to do that as well. That's one of the two types of questions you'll have on the test. All right, the Doppler effect, you're going to see a video on this, occurs in radial motion. Okay, that is, if you remember at the beginning, transverse is side to side, radial is towards us or away from us. So we see the Doppler effect from stars and other objects going either away from us or towards us. We don't notice it if they're going from side to side, though. The Doppler effect is defined as the change in apparent frequency of a wave. It's how we perceive the frequency. That object is still giving off waves at the same frequency, but if it's moving towards us, then those waves are getting closer and they appear to be bluer. If it's going away from us, then they appear to be redder or red shifted. So the spectrum would be shifted more towards the red end of the spectrum. To determine the speed of recession of an object, that is how fast it's going away from us, we use this whole big equation here. Guess what? We're not using that at the high school level right now. It's nice to know how they do it, but I'm not going to throw any questions like that in the test at you. Apparent wavelength divided by the true wavelength equals 1 plus the recession velocity, and that's what you solve for, times the true wave speed. So again, blue shifted, objects coming to you, they look shorter. And I demonstrate this by wadding up about 10 wads of paper and tossing it to someone as I walk towards them. I'm still counting 1, 2, every step I'm throwing a paper wad. 1, 2, 3, 4. But because I'm walking towards them, the distance is shorter, so the paper wads are coming to them like 1, 2, 3, 4 faster. However, I do the same thing walking away from someone because I'm getting further away every time I throw it. Now the paper wads are going 1, 2, 3. Now they're coming 1, 2, and 3, and 4. It's slowed down, so the wavelength appears to be, or is wider. So it's more red shifted if it's going away from us. And with that, it's a very short unit. We end it with Snoopy saying, study and prepare. Know this stuff. It's what astronomers use to study the sky.